we are continuing last week's lab, just a reminder. So bring your lab handout from last week, and then you should have completed your lab from the week before, which was the, you did your unknown, or your weights for your gravimetric analysis, and so you should be able to compare the two methods from that. Are we done that? Never, right? We probably were on Friday when we were doing the wave, yeah. Probably so. So, any other housekeeping? Test corrections are due on Wednesday. Don't forget to get those in. We'll try to get those on your midterm grade. Okay? If I don't, I apologize now. But I'll do my best to get them done. It takes a little while to grade those, so to work through them and to assess each individual score and then get that in the grade book. So I'll try to get all of our labs that we have done up to that point also in the grade book. And the midterms will be posted sometime next week. Cool. Yeah. Now that's in a separate place on Campus Web. You guys know that? It's not actually the grade book for the course. The midterm grade is a different location, the official one. But actually for this class, since I'm using the Campus Web grade book, I'll just convert your score over to that. So you can just look at your grade book score. So anyway, any other housekeeping? Any other housekeeping? Got a demo on Wednesday. Does that work? Yep, so we'll do another demo on Wednesday on lighting. Alright, because I'm still trying to illuminate the topic. Oh, that's twice I've used that. Alright, so last time we stopped and we were talking about calculations which involved energy and frequency of light. There's a relationship of Planck's constant to that. And then we were also using an equation which related the wavelength to frequency and the conversion to go back and forth between those using this constant speed of light in a vacuum. And then we also did some unit conversions from meters to nanometers, because when we're looking at visible light, then that would be the appropriate size unit to use. And so we did some calculations. We stopped on this slide, which is related to those topics. And phi, the Greek letter phi, is used to designate the work function. And so work is a type of energy, right? And so that phi value is given in joules. And it's the amount of energy. If we go back a few slides and we look at the surface, there's an amount of energy that it takes to knock one electron loose. Okay, you guys with me? So for one electron to come off the surface of a metal, it takes a specific amount of energy. Now, depending on what type of metal you have, then that amount of energy varies. Okay, now we're talking about a piece of metal in a vacuum and shining light on that, or the photoelectric effect. But this work function is that minimum amount of energy that you need, okay, to get one electron knocked loose. And so if we know the work function, we could actually get to the wavelength of light that we would need to use, okay? Or if we knew the wavelength and so on, then we could calculate the frequency. And then from the frequency, we could get to the amount of energy that would be produced to make sure that we get over that minimum for a particular metal, okay? So we could work that either direction. Your book has you work one from this direction, which is sodium metal has a work function equal to 3.78 times 10 to the negative 19 joules. What is the minimum frequency of light necessary to remove the surface electron? To what wavelength of light does this correspond? So we have a two-part question. So what this is defining is phi which is equal to 3.78 times 10 to the minus 19 joules, right? Which is equal to h nu, right? So if that's the case, then how do we get to the frequency with this? What's H again? Do you guys remember? Planck's constant. So if I take this equation and start rearranging it, 3.78 times 10 to the minus 19 joules divided by Planck's, which is 6.626 times 10 to the negative 34th power. Help me with units on, we're getting to Planck, so it would be 1 over seconds. Joules times seconds, right? So that's the way we would calculate the frequency, right? Anybody have that value? You haven't got a calculator out yet. I'm going to encourage, like I do every time we do math problems, that you guys bust out your calculator and work the problem out, cancel units, practice your dimensional analysis, and set these up. Because am I going to ask a question like this on the quiz or test? Probably so, right? So if you've done a couple of them, doesn't that make it easier? And if you do a few more with your homework, then by then you'll have practiced enough to be able to do them efficiently. All right, so anybody have the frequency yet?
7 times 10 to the
5.7? 10 to the what? 14. Inverse seconds. All right, so yeah, we got there. So now, how do I get from there to wavelength? How do I get from there to wavelength? Yeah, so if we look at equations again, then C equals lambda nu, right? So the speed of light divided by the frequency should give us lambda. I did write that right, didn't I? Yeah, I think I did. So 2.99 times 10 to the 8 meters per second divided by 5.7 times 10 to the 14 1 over seconds. My seconds cancel. I'm left with meters. Yep.
Wait, where did
Oh, that's the speed of light. Yeah, so that's something that I pulled right out of my brain because I've done about 5 problems with it now, and so I have it memorized for this semester. Right? Everybody have that value? What is it? 5.255 times 10 to the minus 7 meters per second. And then, but normally if we're talking about, well, the way we've been doing wavelengths, and we've been giving them in meters per second or nanometers?
nanometers?
Or not nanometers per second, but nanometers or meters. Sorry, I added a second in there. I don't know why. We canceled that, so we didn't need it. So anyway, so I would do that conversion. 5.255 times 10 to the minus 7 meters times 10 to the 9 nanometers divided by 1 meter. And so what is that number? 525. Nanometers. I'll get it right here quick. That should have been it down. Good job. You guys got it? Pretty straightforward. It's just knowing what equation to use, right? So if I have the equation available for you, could you utilize it, ask that same question? That's what I'm asking you. If you use it enough times, you end up memorizing the equation. All right, another equation. So we're going to add to our list up here. And so the kinetic energy of an electron is equal to h nu minus the work function. Okay? H nu minus the work function. Now, h nu is, it's energy, isn't it? H times nu is energy. And so, if I know the frequency in Planck's constant, right, then that will give me energy in joules. And so, now, I have to be over the threshold for this last problem, okay? The minimum amount of energy would be a wavelength of 526 nanometers, or would have a frequency of 5.7 times 10 to the 14, 1 over seconds. That's the minimum amount of energy to get one electron to leave the surface when a photon strikes. You guys with me? But what if I have a photon that has extra energy? Where does the extra energy go? The rest of it's put into kinetic energy. Okay? And so to find the kinetic energy of an electron, we can do a similar calculation to the one that we just did. Okay? And from that, we can find the kinetic energy of a photoelectron that's produced when a blue photon of wavelength 472 nanometers strikes strontium, which has a work function of 4.15 times 10 to the minus 19. And so we're going to take this equation, right? And we're going to find the frequency of that wavelength. And then we're going to multiply it times Planck's constant. And then subtract the work function, which is given from that. And that's the amount of energy that is in excess, right? That would go into kinetic energy. Yeah? No? Maybe? We'll try the calculation and at least get that far. So, what is the frequency of a 472 nanometer wave of light? So let's do that conversion first. What's the first thing I need to do to this? I need to convert it to meters first, okay? And so that's times 1 meter divided by 10 to the 9 nanometers. believe that's 4.72 times 10 to the minus 7 meters. Yep. And so then I would take that and I would convert that to frequency, right? So I'm going to use my speed of light equation up there and rearrange that to C times, or C divided by lambda equals the frequency, right? So 2.99 times 10 to the 8 meters per second divided by 4.72 times 10 to the minus 7 meters. So our answer is 1 over seconds. Our hertz. I can't do that one in my head. I need help.
Six point three three
6.33
times 10 to the 14.
times 10 to the 14. All right, so now we have frequency. Okay, so once we have frequency, then we can plug in to the kinetic energy equation. So the kinetic energy, now what is the kinetic energy of? What is it, what's the kinetic energy that we're calculating? For a single electron, isn't it? Okay, so this is for one electron that we've knocked off of our surface. And with this photon of light, all right, so we have a photon of 472 nanometers. It comes in, and this is our surface, right? And we have a photon that comes in, strikes the surface, and that electron leaves with some amount of kinetic energy. You guys with me? All right, so that's what we're talking about. And so now we've got that equals h nu 6.626 times 10 to the, what's here, Planck's constant, negative 34. All right, so Planck's constant times the frequency that we just calculated. And if you look at your units, this is joules times seconds. And this is 1 over seconds. And so my seconds now cancel, so this term is in joules. Okay? And then we're doing a subtraction. This term is in joules. To subtract, you realize we have to have like units. Okay? So now we're doing that subtraction. And anybody have that value? This term is actually 4.21 times 10 to the minus 19 joules. I separated that out when I was doing this in my office. Yeah, so I just carried this down. I wrote that down and stuff. And, let's see. So we just calculated the amount of energy that it took to knock the electron out off the surface was this amount, right? That's the work function. And so that's the minimum amount of energy to knock an electron loose. Any additional energy would go into the kinetic energy of the electron. And so this is the amount of energy that our photon produced from a 472 nanometer wavelength. So that wavelength coming in gave us this amount of energy plus that amount of energy. This part got the electron loose, this one makes it move. Okay, you guys with me? Yeah.
I have a question.
Yeah.
So like, because I'm not sure, I'm not sure where I went wrong, but I'm getting a different answer.
I have the same, me too, I have the same calculation, I just keep it in, negative 4.15. Positive 19.
To the positive 19?
I have,
No way on that one. So it's a subtraction, so do what? So it's gonna be, so if you do, what is 4.21 minus 4.15? What is that value? 0.06, right? So what you just calculated was this, 0.06 times 10 to the minus 19.
yeah.
You guys catch that, right? Because both of those are 10 to the minus 19.
Yeah.
And so then if I take that and move that decimal place over 1, 2, right?
Yeah, yeah.
Then that becomes 10 to the minus 21st.
That makes sense.
Cool?
Yeah.
So the answer is 6 times 10 to the minus 21. So I'm not sure what the calculators are doing.
I'm trying to decide what I did, because I just typed it in.
So a lot of times, guys, from a practical standpoint, when I'm doing a subtraction and I have both the numbers in the same scientific power notation, right? When they're the same, I don't do anything with the times 10 to the whatever, right? If they're in the same power, I just subtract the two numbers and then do exactly this, right? And just write that number down like that. And then I make that next step to move the decimal place to get one digit in scientific notation to the left of the decimal. Okay?
Usually, like, if you're not getting the right answer,
Yeah.
put the whole 4.21 times 10 to the 19, put that all in one parenthesis.
Yeah. Well, are you using the engineering notation button, the E button, when you do the powers of 10?
I think what I,
No.
I think okay.
So if I do like 10, right, and then go second E, does it E? Okay. Right? Yes. That should be this number right here. And that should be 4.21 times 10 to the minus 19.
Yes, it comes out 4.19.
Maybe I miscalculated.
That's what I'm saying.
I mean, I don't know.
I got that too on mine.
I did it again.
What's that?
The 6.9 watts.
The 4.21 times 10 to the minus 19? I don't know. I don't know, because that's the way I would do that. So I'm not sure what's going on.
Are they in parentheses?
The 4.19.
So it's rounding it down by 2 units. That's so weird.
I don't know. 'Cause I didn't do it on the pad.
Are you putting those numbers in parentheses, or is that what the parentheses on?
Yeah, you can watch.
So are you keeping all your sig figs, the 626 out?
That's what I did, like I rounded my shit slightly different.
If it's a little off, I don't have a problem. He's off by 2 digits, which is weird. I'm not sure. I don't know what's going on there. That's the first place I would look. Huh?
Yeah.
Mine was that too.
4.43.
Yeah. Mine's 4.4. Yeah.
Huh.
Like, and I.
I'll go back through one more time in my office and see if I come up with the same thing.
I think somebody some people don't put the 8 on the multiplier for
The
speed of
speed
light.
of light.
All of
Yeah,
that.
and that's what's causing the discrepancy.
Huh.
Some only go to 3 and some go to 4.
Well, we're close. All right. Couple units at 10 to the minus 19. That's within the experimental error. Exactly. All right. That's what we'll go with anyway. I'll look at that. I'll look at it again and see if I calculated the same. And I'll do it one more time. All right. This part may be a little bit boring.
That was the fourth time you did that?
At least I'm trying. I at least have half of us got it this time. So, do what? You didn't get it that time? Read the title.
I get it now, but.
Oh, you didn't get it the other times. Yeah, Bohr, yes. Bohr, he actually was amazing. He was a physicist. I want to throw that out there right now. There's actually a great movie. It was a play that was done, and it's called Copenhagen. And if you take chemistry as a major, then you'll get to watch it in physical chemistry. Okay, I started that years ago, and it's a hypothetical conversation between Bohr and another scientist called Heisenberg. Okay, and Heisenberg was German, right? Bohr, I believe, was Danish, and he was Jewish. Okay, you guys realize that this story rolls up into World War II, and Heisenberg worked under Bohr. So the story goes, Heisenberg was in the audience and Bohr was presenting a paper on his understanding of physics and quantum mechanics, and a young 17-year-old Heisenberg in the audience raised his hand and said, "Sir, that can't be correct. Your mathematics are wrong." And Bohr's response was a good, mature, scientific response. "Well then, sir, please come to work for me and show me where it's wrong." And so Heisenberg went and worked with Bohr to show him what was wrong. A few years later, the war started. Okay, and guess who ended up in charge of the nuclear program for Nazi Germany? Heisenberg, right? So during this period of time, Heisenberg went and visited Bohr, and there's a play written about the conversation that happened in Copenhagen. And so, and it goes through different iterations of what could have happened. And it's in the library, it's on DVD. You guys may not know what that is, but you might also be able to find it online. But if you're not going to take physical chemistry, I think it's worth watching. And always in my mind, when I watch it, I think that maybe the reason that the Germans didn't get a nuclear bomb was because Heisenberg didn't give the critical mass number to know how much they needed to have to make the bomb explode. And that's a very basic calculation. And his understanding of it was probably significant as much as anyone in the world. And so always in the back of my mind, you wonder if Heisenberg is maybe responsible for change in history, because the Americans were able to develop it first and then use that on the Japanese to end the war. Interesting thought, isn't it? Things that happen that we may not realize that may be truly significant in time, but unless you study or look at that or read a little bit of commentary about plays that you just randomly saw on PBS and thought your students should see it, right? Yeah. So anyway, just throwing that out there, that Bohr gave a lot to science, and maybe his relationship with one scientist named Heisenberg may have changed the world and world history. We might all be learning in German right now. What a thought. So, anyway, light and matter. Gosh, this is so much fun. And we're going to do some really cool demos next time. And we actually have an online version, but it's much better live in my mind. So, when gaseous atoms of an element are heated to very high temperatures, they start emitting light. Okay? If we throw a whole bunch of energy in, then it happens. You guys see this all the time in fireworks, right? Are there different colored fireworks when they shoot up in the sky? Quite amazing. They do that with different metals, different elements. And so each metal has a unique spectrum. And, well, it's inconsistent with the Rutherford model for the atoms. And so Bohr was the first one who gave a partial explanation. Let's see if this actually opens. Yeah, I couldn't do that earlier. I don't know what's wrong with it. So anyway, that's flame tests. And so this just shows different videos of flames burning in different colors. In fact, there's a practice question online that in the homework where you use this figure to do flame tests and predict what metal it is based on the color. Well, we can actually use instrumentation to look at that, or even use a prism or a diffraction grating to split the light up into individual wavelengths. And so this is a photo of Bohr, Niels Bohr, and he won the Nobel Prize in 1922. Electrons must be found at only specific distances from the nucleus in orbits, and electrons travel in circular paths in discrete energy levels, and each element has a unique set of energy levels. Now, he is correct in a couple things here, okay? Number one, it is absolutely true that each element has a unique set of energy levels, okay? That is very true and very specific. The problem is that those electrons don't travel in circular paths, okay? And in fact, Heisenberg's uncertainty principle is what helped modern quantum mechanics come about, okay? And so that we can't know the exact location of an electron in its relationship with the atom, and so that it's moving randomly in that. And then we use probability mathematics to predict the amount of energy it takes to move from level to level. And so anyway, and so he got that right. And electrons are found only at specific distances. Well, it's not exactly true in that, but it is found in orbitals, okay? And so they're randomly moving within those orbitals, that regions of space. Now, what's funny in my mind is that they really don't have to be inside those orbitals. They can move outside of them, but it's calculated there's a probability that they exist there, okay? And so in an s orbital, they predict that's a spherical shape, and it will be somewhere within that sphere region that electron moves. And then p orbitals are dumbbell shaped, and they have three axes, x, y, and z, and those electrons would reside in those, and well, they reside as pairs, and there's all kinds of fun stuff that we have added to this from Niels Bohr time, all right? So, but in 1922, he used this to explain emission spectrum, all right? He could only do it for one element, hydrogen, and then what he did was he said there was a nucleus, right? And around that nucleus, we have orbitals, and he put those in as ring orbitals, right? And he said an electron would, if I only have one electron, maybe she's an E there, and that electron would, at its ground state, lie in that ground state level, that lowest energy level, right? And then if a photon comes along and excites that, and that electron can move up to a new energy level. Now, we just learned something about photons, right? Different wavelengths of light have different amounts of energy. Would you guys agree with that statement? And can we calculate that amount of energy with some very basic calculations? Yeah, and so what we know is that the energy, right, of the wavelength, right, we can get that. So then if we have a photon that comes in and moves it from the ground state to the first energy level, right, then we know the amount of energy that it took to do that, right? Or if we excite it to the second level, is that going to take more or less energy to go from the ground state to the second level? It's going to take more energy, right? And so that what we're talking about is absorbance, aren't we? So we're talking about energy that's being absorbed. But now what happens if I get an electron and it's residing in an excited state in the second energy level and it goes back down to the ground state? What happens? We get emission, don't we? And the emission, right, is going to be the same energy that it took to get it from the ground state to go up. Right? And so we're going to get emission. Now, that's not always true, because what would happen if I go from the ground, or from the second state, right, down to the first excited state? Would I get a different photon? And in fact, this one would be less energy, so it's going to be a longer wavelength. You guys with me? Right? So this one's shorter because it's in higher energy, right? Or higher frequency, lower frequency, if you want to look at it that way. And so the farther I go from the nucleus, right, the more energy it takes, up to the point the electron's ejected and no longer influenced by the nucleus. Right? And we know the energy values to do that too. So anyway, ground state and excited states. Okay? Ground state and excited states. So this is kind of fun. All right, you guys ready for it? Here it comes. Maybe dangerous. I don't know to who in this classroom, but be careful. I'm going to collect this, and it's going to be dangerous. Just told me that. Here it is, here it is. Wait for it, bang. Wait for it. Oh, we need to do that again, don't we? All right, so here comes the photon. Here it comes. Bang. Cool? I mean, it's almost as good as my drawing. Oh. I'm right, I didn't close it. Thought I had it. All right, now, I've already given the answer this way. How many photons of light will be emitted when an electron falls from the third energy level directly to the first energy level? So we got to go out one. So the electron goes from out here, all right, down to here. One photon, right? And that would never get a photon. Let me try again. Cool. Now the next one says when an electron falls from the third energy level to the second, and then from the second energy level to the first in a two-step process. How many photons are emitted? So now what we're doing is our electron is going down to here, and then a second step it's going down to here. So this is where it's going to end up. 2 photons, right? One for the first step, one for the second step. Okay, you guys cool with that? Yeah. So anyway, Now, one electron for the bigger step and 2 photons. Now, I have a question. All right, I have a question. Which of these photons will have the highest frequency? The one from here, the one from here, or the one over here? Which one will have the highest frequency if we're talking about the same atom? The single one from 2 steps or either one of the individual steps? This one will have the higher frequency. It'll be higher energy, won't it? It will be a shorter wavelength, okay, than either one of these, because this is the same amount of energy just done in 2 steps. Okay? Same amount of energy just done in 2 steps. Okay? All right. Here's some nice examples, and we're going to look at these actually in class next time. Okay? So we're going to do some emission spectrums, and I'm going to bring a hydrogen lamp and a helium lamp and a neon lamp, and we're actually going to observe these with our own eyes. Okay, that'll be fun, won't it? And then I'll bring a spectrometer. Anybody know what this sign is made out of? Neon lights, right? Now, actually, the coffee part is neon. What about the blue part? Is that neon too?
No.
No, that's another element to make blue, okay? Or combination. And so that is not neon, and it's just a different element inside of a type of bulb. And so if we're looking up here, hydrogen, if we notice in the visible part of the spectrum, how many lines does hydrogen have? Has 4 lines. Helium, does it have more lines? It does. It has 1, 2, 3, 4, 5, 6, 7, 8 lines in that same region. What about neon? Does it have more lines in the visible part of the spectrum? Now, I have a question. Can there be lines outside of the visible part of the spectrum? Yeah, if you have the right kind of eyes, can you see those lines? Yeah, so you need a spectrometer that can see either into the infrared where some of the lines would exist, or in the UV part of the spectrum where others would exist. So when we're doing single element lights, then sometimes it may not be wise to stare at them for long periods of time, right? So depending on what they are. All right. Rydberg's equation. So the Rydberg's equation is a calculation that was developed by Bohr and other scientists to describe the energy levels that I'm erasing right now. I don't know why I'm erasing them. I got started, and so we're just going to go ahead and erase it. And go over here and write on the right side, or the left side of the board, the Rydberg constant, which is and so if I look at the equation up there, the Rydberg equation, and what we find is that the Rydberg constant RH times 1 over the energy level N of the first wavelength, or the first level, to the one that is transitioning from, and so into, and so anyway, so this is an equation which we can calculate the wavelength from, right? This is actually the inverse wavelength, but it's called the wave number. Okay, 1 over the wavelength is called the wave number. But if I'm looking at this relationship, then I can use this to calculate the energy between levels for hydrogen. Okay? All right, and so if I'm doing that, then calculate the emission of photon that is emitted when a hydrogen atom drops from the 4th energy level to the 3rd energy level. All right, from the 4th energy level to the 3rd energy level. Is this photon is this photon in the visible region. Okay, so that means that we want to calculate, we want to ultimately find the wavelength. That's our goal in this, okay? And so this is equal to 1.097 times 10 to the 7 meter, 1 over meters, and 1 over 3 squared minus 1 over 4 squared. Oh my gosh, can't write. Brain and hand have been connected all day.
Does it matter which energy level you go for?
So we're starting on the, it's dropping from the 4th energy to the 3rd level. It would be this, the difference between the two. One would be a negative energy and the other one would be a positive, but I think it would be the same magnitude. And so then you would know whether it's coming off as a photon or adding in that relationship based on the way that this is the emission. Do you have that number? Yep.
Would be 5.333 times 10 to the 5th.
What do you guys think? Is that it? How do I get the wavelength? So this is 1 over wavelength. What do I do? So if I take this and go 1 divided by 5.33 times 10 to the 5th, 1 over meters, that means the meters moves upstairs. And so lambda equals the inverse. And I'll know that if that's the right answer when you give me that value. Got about a minute. I'm going to cheat. And so 5.33 times 10 to the 5th, 1 over meters. And then when I invert that, then I get 1.875 times 10 to the minus 6 meters, or that's 1,875 nanometers. And I have a question for you. Is 875 nanometers the visible part of the spectrum? No, it is not. And so that is, which part of the spectrum is that? That's longer than visible. That's longer than visible, so that's less energy than visible. And so what part of the spectrum am I in?
Infrared.
Infrared. It's actually would be infrared would be where that one's at. Okay? Cool? Yeah. Where's microwave though? What's up? Remind me to do this slide. Driver, which one more try.